Shale Gas to Gasoline by Toby, Sarah, and Jacob. So for the background, gasoline is an essential compound both for consumers and commerce. Shale gas is in abundance in the United States, and the Haynesville Shale in Louisiana is a large source of shale gas located in our parish. So we're here in Lincoln Parish, which is where Louisiana Tech is, which is right on part of the Haynesville Shale. So current shale gas composition is 95% methane in Haynesville. We're really going to be looking at Haynesville. They vary between patches between, like, let's say Illinois Shale is different than Louisiana Shale, which is different than Indiana Shale. So for the Haynesville Shale, it's 95% methane, 0.1% ethane, 4.8% carbon monoxide, carbon dioxide, and 0.1% nitrogen. And really, so the Haynesville Shale in particular is very rich in methane. Sometimes you'll get around 80% methane and 10% ethane, but for the most part, the Haynesville Shale is methane. So in order to convert shale gas into gasoline, we will be using the model compound methane, which consists, as we previously mentioned on the last slide, of about 95% of the Haynesville Shale's hydrocarbons. So what we're first going to do is we're first going to couple methane via non-oxidative coupling into ethane, and then we are going to do non-oxidative coupling of ethane into butane, and then we will use butane aromatization to create gasoline by using aromatics as a high-octane gasoline fuel. And that will allow us to convert shale gas into gasoline for vehicles.
The first paper we selected was titled Highly Selective Non-Oxidative Coupling of Methane over Platinum Bismuth Bimetallic Catalysts. This paper showed a 90% selectivity in conversion of methane to C2 species at 600 to 700 degrees Celsius. The second paper we selected was titled Non-Oxidative Coupling of Ethane with Gold-Loaded Catalysts. This showed a direct and continuous conversion to N-butane and hydrogen at 47 degrees Celsius. This reaction used gold-loaded gallium oxide and titanium oxide photocatalysts. Butane production rate using titanium oxide was 0.65 micromoles per hour and selectivity was 89.3%. The third paper we selected was titled Aromatization of Butane via 1% platinum, 1% germanium over HCSM5. This paper showed a 100% conversion of butane to aromatics, and the aromatics can be used as a high-octane gasoline. This reaction occurred at ambient pressure at 550 degrees Celsius.
So currently there are two knowledge gaps which our proposed process will fill. The first one being that applications of shale gas are currently limited mostly to the energy sector, and by such we mean right on the site. So for example, direct combustion for steam, which can then be used for power or just direct electricity generation on site, as opposed to more valuable commodity items. And the U.S. transportation sector relies heavily on drilled or imported crude oil, which is refined into gasoline in an environmental and energy-intensive process. So this technology will fill these knowledge gaps by providing a value-added product from shale gas, as well as making the U.S. motor pool more sustainable by using shale gas in the United States as opposed to having to go out and pollute the sea, transport things across the country, refine it and all that. You can essentially have an on-site sustainable technology through our proposed process.
We know our technique is possible because the methods and processes are well established in literature. Shale gas is currently an underutilized source of energy in the United States. Two of its biggest draws are its price and its abundance in nature. Domestic energy security can be fostered through developing new uses for American shale gas. Safety, both personal and environmental, are important when discussing oil and gas. Shale gas is on the whole safer than offshore liquid petroleum mining. Oil spills can be avoided when using shale gas. Deep sea drilling equipment can also be eliminated when using this resource. One of the draws to our technique is that our proposed process has only one multi-phase step, that being aromatization.
Various amount of materials are needed to help aid in the process of shale gas to gasoline and the conversion. And so for the first step, which is the non-oxidative coupling of methane, chloroplatinum acid hexahydrate, bismuth chloride, and ammonium ZSM5 are needed to create the bimetallic catalyst, and these can be obtained from Sigma Aldrich. For the non-oxidative coupling of ethane, which is the second step into this process, anatase titanium oxide, rutile titanium oxide, and tetrachloroaurate 3 hydrate can all be found from millipore sigma. And then for the butane atomization, transdiamine tetrachloroplatinum 4 can be obtained from Sigma Aldrich. ZSM5 support material can be found from Sigma Aldrich or ACS. And then tetraethylgermane from millipore sigma and hydrogen gas can be used to create the platinum germanium catalyst needed for the atomization.
Chloroplatinum acid hexahydrate and bismuth chloride precursors were used to obtain the platinum and bismuth metals for the catalyst. To start, the ZSM5 ammonium form was converted to H form by calcining in air at 500 degrees C for 4 hours. The platinum and bismuth were loaded sequentially with wet impregnation. Platinum and bismuth were dissolved in dilute hydrochloric acid and added dropwise to the stirred ZSM5 slurry. This mixture was stirred for 8 hours at room temperature. This was then rinsed and dried at 100 degrees Celsius before use.
To synthesize this catalyst for non-oxidative coupling of ethane, photocatalysis is used. And so to prepare the catalyst for this process, photodeposition method is used. And so tetrachloroaurate 3 hydrate is used as a precursor for the gold element to be loaded onto titanium oxide. Now first, titanium oxide is dispersed in deionized water, and this suspension is photoirradiated for 30 minutes or so. Then methanol and a required amount of the gold precursor is added to this suspension and stirred for 1 hour in the dark. Now after stirring this suspension, then it was photoirradiated using a ceramic xenon lamp for around 30 minutes, and after 30 minutes was up, the powder was filtered, washed with water and ethanol, and dried in an oven at around 370 degrees Kelvin overnight.
So to create our catalyst for butane aromatization, first ZSM5 is protonated by hydrothermal ion exchange with an ammonium ion and is then calcinated in air at 823 Kelvin. Then platinum is now loaded onto the ZSM5 zeolite by ion exchange with transdiamine tetrachloroplatinum 4 precursor and is then calcinated in air to obtain platinum 3.8% loading on HZSM5. Then chemical vapor deposition was used to create the platinum germanium HZSM5. This was done by first loading the platinum ZSM5 and reducing it with flowing hydrogen at 673 Kelvin. And then germanium precursor was vaporized at 493 Kelvin across the material for about an hour. And this step would be where you would vary the amount of gas, which would in turn vary the loading of germanium onto the catalyst. And then after reducing it in hydrogen again for 1 hour, you'll get your catalyst that you can use for the aromatization of butane.
H2O2 chem absorption can be used to determine the number of metal surfaces, as this is the most precise. XRD can be used to determine the crystal structure as well as other geometric properties. TEM can be used to take pictures of the catalyst and determine the particle size. BET can be used to determine the surface area and porosity, but this can only be used on our second catalyst, as this will not work for zeolite-based supports.
Different methods could be used to record catalytic performance and kinetics for the process in converting shale gas to gasoline. To measure the kinetics and the spectator analysis, an FTIR could be used. Then a UV radiometer could be used for any photocatalytic reaction test, especially for the non-oxidative coupling of ethane, which uses the gold-loaded photocatalyst. Then online gas chromatography could be used, and FID could be used because of all the hydrocarbons present, and using FID could increase the precision and sensitivity in those analysis and recordings.
So our expected results include that we would see the mean size of the hydrocarbons increase throughout different stages of the process. So, methane will become ethane after the first reaction, ethane will become butane after the second reaction, and then once passing through the third reactor, we would get aromatics from the butane. Coking and deactivation also need to be avoided, as well as overoxidation and the formation of CO in the system can cause catalyst death. And aromatic building blocks are target compounds for this experiment, which can be directly used as high-octane gasoline or for further coupling to form diesel or other fuels. So we have 3 reactors for our initial separation of products. So we're first going to have our methane coupling to ethane, which is then coupled to butane, which is then undergoes aromatization. And then since we have a gaseous and solid products, we're going to have a simple flash drum, and you can have your liquids recovered, your aromatics that you can use for your gasoline, and then all your gaseous stuff come back around with a purge on hydrogen and your compressed shale gas feed coming in. So for process intensification, the first thing you can start with is heat integration. So we have our compressor, which is compressing the extracted shale gas. We then put an intercooler on it to recover the heat to use on other processes. And we can do the same here for our liquid product stream here, which will also recover heat that can be sold or used other places throughout a chemical facility, say in an air separations plant or even just general heating. And then we would also, these 2 red cylinders here and here represent membranes, which can be made of polysulfone with a high permeability of hydrogen, so that we can recover as much hydrogen as possible. And then use this gaseous hydrogen, we can burn it in fired heaters for the reactors, sell it as hydrogen gas, or just burn it again as energy throughout the plant by providing steam or other mechanical work.
Our technique is not only possible, but shows great promise for the future of clean energy. We can produce more gasoline while extracting less fossil fuels out of the ground. A safe and effective process can be developed for the conversion of shale gas to gasoline without excess difficulty. The conversion of methane to gasoline will become more common as shale gas mining is increased in the future.